Tēnā koutou katoa. Welcome to this video about equilibrium principles, intended as revision for Level 3 NCA or for a summary of Level 2 equilibrium principles. Equilibrium starts with realising that reactants combine to form products, but the products also undergo the reverse reaction to reform the reactants. This can be seen in the following reaction, where in the forward direction, nitrogen and hydrogen combine to make ammonia, but at the same time in the reverse reaction, the ammonia reforms hydrogen and nitrogen. Dynamic equilibrium can be said to exist when the rate of the forward reaction and the reverse reaction is the same. The equilibrium constant, symbol Kc, is a number that represents the ratio of products to reactants at equilibrium. Remember, this is when the rate of the forward and the reverse reaction is the same. Take a look at these instructions here. They show that for any equation where you've balanced it using the lowercase letters, you use those to raise to the power on the right-hand side where you see in red the equilibrium constant expression. It might be easier to look at the bottom reaction, which is an example of this. And you can see that the 4 that is needed to balance the NO2 now becomes a power in the equilibrium constant expression on the right. Other important things to notice is that you multiply the different components, not add, that the square brackets refers to concentration in moles per litre, and that this means that liquids and solids are not included in the equilibrium constant expression because they don't have a concentration. You only include gaseous or aqueous components. Probably the best way to have a go at this is to try some examples for yourself. So here are a few practice questions. What I'd like you to do is pause the video and write the equilibrium constant expression for the first 3. And for the last one, try and write the equation that it came from. So pause the video now. Okay, you should have had a go at these now, and the answers are coming up on the right-hand side. Check your answers and make sure that you have got this concept because it's quite important. Note carefully a couple of things. In the third equation down, H2O was a liquid, so we don't include that in the equilibrium expression. The W in the same expression just refers to water. The K is the most important bit, so don't dwell on this too much. And lastly, note that in the bottom equation, it's okay not to have the states in. You could have an educated guess if you like, but you can just leave those out. Let's take a look now at what the actual value of Kc means. You can see by this diagram here that if the K value is really small, so we've got a number of less than 10 to the power of -3, that tells us that we've got a lot of reactants and not many products. So we say the equilibrium position lies to the left in this case. Think of this mathematically. If we've got a larger number on the bottom and a small number on the top, that gives us a tiny number. If the K value is around 1 or some kind of intermediate value, that tells us we have around the same amount of reactants and products seen in the middle there. And if the K value is very, very large, that tells us our reaction is product dominated and the equilibrium lies to the right. So just to reiterate that equilibrium does not mean there is equal amounts of products and reactants. This is a really important point. The next thing you might have to do is do some calculations of equilibrium constants, such as this question here. Pause the video now and have a good look at this question. We'll take a look at how to answer this on the next slide. Let's now go through how to answer that question. The first thing you need to do is write the Kc, or equilibrium constant expression, for the equation. Then you need to substitute the numbers in at the right spot, 0.105 for NH3, 0.0821 for N2, and 0.0583 for H2. And don't forget to raise each number to the correct power. Doing this, we get the answer 677, which is not the same as the given equilibrium constant of 640. That means this reaction is not at equilibrium because the two numbers aren't equal. The next big part of equilibrium is to look at Le Chatelier's principle. Excuse my French. This principle states that if a change is imposed on a system at equilibrium, the system will react to oppose that change to restore its equilibrium. And there are 4 different changes that we will study that we can impose on the system. These are concentration, pressure, temperature, or the use of a catalyst. Let's start by looking at concentration. And just a note, try not to memorize everything that's written in these slides. Just try and apply the general principle. In terms of concentration, here are a couple of examples. If we increase the concentration of reactants, the system will shift in the opposite direction, i.e. to try and decrease the reactants. And this is a shift to the right. Looking at another example, let's imagine that we decrease the concentration of the products, i.e. removed products. This would also produce a shift to the right in an effort to increase the products and do the opposite to the change that we imposed. Let's look at this in a different way. Consider this reaction. If we add ammonia to this, that increases the products, the equilibrium is going to shift left to oppose that change. Let's take a look at this in a graphical way. You can see where the arrow is, where the change is imposed. The green graph of NH3 ammonia increases sharply, showing that that is the change we've imposed. And then as we move across to the right, we can see how the system responds. H2 and N2 increase as the equilibrium shifts to the left in response, and NH3 decreases as the equilibrium shifts left in response. Let's now look at the change of pressure. First, we need to understand what pressure is. In our case, pressure is caused by gas particles moving around in a closed container. As they collide with the sides and with each other, they create pressure. We can change the amount of pressure by changing the volume of the container. Making it smaller will increase the pressure, and making it bigger will decrease the pressure. We can also change the pressure by changing the moles of gas. If we have more moles of gas particles, that will increase the pressure by increasing the collisions. Note that the size of the gas particles is irrelevant here. So we can look at 2 changes that we can impose in terms of pressure. We can decrease the volume to increase the pressure and increase the volume to decrease the pressure. Let's first consider when we make the container smaller to increase the pressure. Looking at the equation above, we can see that there are 2 moles of gas on the left and only 1 mole on the right in green. So, as we have increased the pressure as our change, the system wants to oppose that and decrease the pressure. And the only way it can do this is to move to the right to make fewer moles of gaseous particles, shown by forming green particles here. If you look at the other side, if we decrease the pressure, the system could only respond by moving to the left to make more moles of gas particles and increase the pressure in this way. And this is shown in this diagram with more red particles of gas. Let's take a look at how we could write an answer about how a system responds to a change in pressure. Consider this equation here, and the change imposed is that we decrease the volume of the container at the point shown. The first thing we need to state is that decreasing the volume of the container increases the pressure. If the pressure is increased, the system must respond in the opposite to decrease the pressure. To decrease the pressure, the system needs to move in the direction that has the fewest moles of gas particles. In this case, the right-hand side has 2 shown here, and the left-hand side has 2 plus 1 is 3 moles of gas. So the right-hand side has the fewer moles of gas. This means the equilibrium shifts to the right. And the last thing we need to state is that this shift means the amount of products increases, i.e. we get more SO3. To assess the effect of temperature on an equilibrium system, we must know if the reaction is endothermic or exothermic. Remember, exothermic reactions release heat to the surroundings and we see a temperature rise, whereas endothermic reactions absorb heat from the surroundings and we'll see the temperature fall. Taking a look now at a specific reaction, in this reaction pink cobalt ions are added to chloride ions to make blue cobalt chloride complex ions. The equilibrium system is set up in each of the 4 test tubes. If we know that the forward reaction is endothermic, then what we can do as a skill is to think of heat as a reactant or a product. In this case, it would be a reactant, as endothermic means heat is absorbed. So we can just write plus heat on the left-hand side, as you can see here in the equation. So how do we write an answer like this down? Remembering our reaction here, we take one of the 4 tubes at equilibrium and put it into a beaker of warm water, remembering that heat is a reactant in this case. So let's start our answer with a statement that the change imposed is an increase in temperature. Let's then link that to the fact that the system responds to do the opposite, i.e. to decrease the temperature in order to return to equilibrium. Let's link that to the direction that the system would move to do that. In this case, the system is going to move in the endothermic direction because that's the one that decreases temperature. And in this case, the endothermic direction is the forward direction, as we've already stated. So in this case, we will see more of the products as we're moving to the right. We will see more blue cobalt chloride. And lastly, let's look at the effect that a catalyst has. On the left, with the line in green, you can see that a catalyst provides an alternative pathway with a lower activation energy, which results in the graph on the right. The catalyzed line in green has a faster rate than the uncatalyzed line. But note that the 2 reactions reach the same equilibrium position. The catalyzed reaction just gets there faster. So a catalyst does not affect the position of equilibrium. It just speeds up the forward and reverse reactions equally. So far, we've looked at the changes and their effects on the direction of the equilibrium shift, but we could be asked to consider the effect that those changes make on the number, the value of Kc. The important thing to remember is that the only thing that changes the value of Kc is a change in temperature. The concentration changes, it doesn't change the Kc. If the pressure changes, it does not change the Kc. A catalyst obviously doesn't either. Only the temperature changes the Kc value. Let's take a closer look at temperature. Remember that the Kc is a value of products divided by reactants at equilibrium. This table summarizes all the possible changes that we could make to temperature and what would happen to the Kc. But let's take a look at this particular reaction here. The forward reaction is exothermic, so that means we can put plus heat as a product on the right-hand side. Now consider what would happen if we decrease the temperature. That's why I've put the arrow in blue. If we decrease the temperature, the system would respond to increase the temperature. And to do this, it would move to the right where heat is released. And moving to the right, it would make more products, and therefore the Kc would increase. Mathematically, you can see the increase in Kc as I've drawn a large products over a smaller reactants as everything is moving to the right. And that's the end of this video on equilibrium. See you later.